Hello everyone, my name is Joshua Powers, and on behalf of my co-authors, I'll be presenting Morphology Dictates Learnability in Neural Controllers. Consider a neural network being optimized for some task. It has an optimal solution space, theta star shown in blue, where every point represents an assignment to the neural network weights that solves the task. Theta in red represents all other possible assignments. An avid area of research in neural networks focuses on moving quickly from theta to theta star. We postulate that at least one determining factor in this goal is the ratio of theta star compared to the total space theta. Let's define a metric that represents this, called the learnability metric, M sub L. Another related problem in neural networks is called catastrophic forgetting. Here we have multiple tasks, A and B, that we wish to solve each with their own optimal parameter spaces. Often in sequential learning, if we have found an optimal parameter set for A, when we go to learn B, we follow the white path to get there. And thus in learning B, we forget A. Here we wish to find a set of overlapping parameters that solve both tasks. Let's define a metric, M sub Cf, that represents the likelihood that a solution to A is also a solution to B, and call this metric a network's resistance to catastrophic forgetting. The traditional focus of research in this area is what we would call brain-centric. It focuses on either developing new learning algorithms or focusing on new neural architectures that improve either the learnability or the resistance to catastrophic forgetting over some task. In this study, our focus will be to manipulate the aspects of a robot's morphology. We theorize that different morphologies will have different characteristic parameter spaces, thus making some morphologies more learnable or some more resistant to catastrophic forgetting regardless of the neural architecture or the training method used. To test our theory, we create a standard robot design with 2 motorized wheels and 2 light sensors and challenge it in a phototaxis task. With the robot at the center, we test the robot in 4 different environments, A, B, C, and D. The morphology of this robot is determined by the placement of its light sensors on the surface of its body. In each environment, we sweep over both network parameters and over 6,000 morphological designs or sensor placements, and measure both the learnability and the resistance to catastrophic forgetting for each morphological design. To test the generality of our results, we use 2 different types of simulations. One is a mathematical model based on using differential equations. The other we simulate in the Open Dynamics engine. Here is the parameter space for the baseline hand-designed morphology. Here in cyan, we can see the optimal parameter space of the standard design. As can be easily seen, the space in cyan is very small, and this robot scores poorly on both metrics. In contrast, here is the space for one of the best designs. As you can see, the learnability metric of this robot is much greater. Also, it has high resistance to catastrophic forgetting. With this robot design, it is very likely that if you learn to solve even one of the environments, you will have also solved all of the environments. We can show these results again for the baseline morphology with the physics simulation. Here it is hard to find the cyan space or the optimal parameter space, but there is exactly one cyan dot in the very bottom right-hand corner. In other words, there is only one set of parameters for this robot design which was able to solve all 4 environments. Just as in the mathematical model, the standard morphology scores very poorly on the metrics. This is one of the best morphologies in the simulated environments. Notice that this is the same design that was found in the mathematical model. Here again we can see that the optimal space has become much larger than the standard design, though not as great as in the mathematical model. This robot does much better under our metrics than the standard hand-designed robot. So one question might be, how rare are these high-performing designs compared to the standard ones? Here are 2 density plots where the x-axis is the score over the metric, and the y-axis is how many robots there were with that score. Thus, designs to the far right of the graph are much better than designs on the left. The best morphologies shown with unintuitive designs fall on the furthest right positions, and other designs that perform similarly are very rare. The standard design that was hand-designed falls to the far left, and there are many such designs, intuitive and unintuitive, that perform just as poorly. Overall, we feel that this shows that not only does the design of a robot drastically change its optimal parameter space, but that hand-designed robots are unlikely to exhibit this desirable feature. In other words, if we consider a hand-designed robot to be a sample from this space, it is very unlikely that a hand-designed robot would be an optimal robot over these metrics. Thus, our results provide strong motivation for furthering the field of automatic design in robotics. Our results show a strong connection between a design and a robot's optimal parameter space. However, we feel future work could further solidify and reinforce this message. Thus, future work would involve testing these designs while actually learning the network parameters. We also want to use larger neural networks and more complex morphologies in the future.